Hi everyone, welcome to this video. In this video, we will be discussing the basics of Navier-Stokes equation. So we will review whatever we had derived in class. Uh, the derivation of Navier-Stokes equation is important because within the derivation we introduced several concepts. So in this video, we will go over one by one on different concepts we have discussed in class. Then we will specifically discuss the shear stress tensor in more detail. This analysis is supposed to sort of help you understand the origin of shear stress tensor and touch upon few things that we had to sort of leave due to the time constraints in a lecture. So let us start by going over through the Navier-Stokes equation. So the Navier-Stokes equation, as you will recall, is only for constant rho and constant mu, or the density and viscosity are constant. So please remember this, that you cannot use Navier-Stokes equation whenever mu is not constant. Whenever viscosity is not constant, you have to go back and use Cauchy momentum equation, and we have discussed one example in class already. So the Navier-Stokes equation has the left hand side is rho del v vector by del t plus v dot del v vector, and the right hand side is minus grad p plus mu del square v vector plus rho g vector. So let's go term by term and discuss whatever we have discussed in class. So let's take the left hand side, which is rho del v vector plus v dot del v vector. So the LHS is rho del v vector by del t plus v dot del of v vector. So as you can recall, in class we have discussed that Navier-Stokes equation is nothing but Newton's second law. Basically what we are trying to do is we are trying to write force balance on a fluid element. So this cuboid shown here is basically a element like delta z, delta y, delta x, so on which we had written this balance. So the left hand side was actually the mass times acceleration part of the Newton's law. So Newton's law is basically summation of force is mass times acceleration. So this rho del v by del t plus v dot del v vector is this mass times acceleration part. However, we are doing per unit volume basis. So mass times acceleration actually become rho times acceleration. So that's why there is a rho here. And this del v by del t is actually del v by del t plus v dot del v vector is actually acceleration, and as we had discussed in class, this is actually the substantial derivative of velocity vector or the material derivative of velocity vector. So if you sort of are not able to recall about this material derivative or this part of the equation, basically recall that we had basically done a balance of that acceleration rho a vector is the rate of change of momentum plus net outflow of momentum per unit volume. Okay, because everything is per unit volume. So you can remember from your freshman physics that mass times acceleration is actually or net force is actually rate of change of momentum. But we also said that in fluids it is not just rate of change of momentum, it is rate of change of momentum plus net outflow of momentum, and that is because our system, which is like a fluid element here, has open surfaces that momentum can come in, momentum can go out. So what we did was that we wrote in the lecture, we wrote momentum, rate of change of momentum plus net outflow of momentum per unit volume in x direction, and you can imagine that the rate of change of the net outflow of momentum can come from all the six surfaces. So for instance, on this top surface, mass may be flowing in this perpendicular to the system, perpendicular to the surface, but it will still have some velocity in the y direction, so it will have some momentum in the y direction. On this surface, on the side surface, the mass may be coming in perpendicular to this and the velocity may still have y component, so this will also be in a y component of outflow of momentum. So we did this in x direction, you can do it in any direction, and then we generalize this part of the equation. And what we said was that Del V by del T is the standard rate of change of momentum part. The net outflow of momentum is this V dot del V vector part. Okay, so just do not forget that LHS of the Navier-Stokes equation is rho A vector, where A vector is this del V by del T plus V dot del V vector, or the material derivative of velocity del capital D V vector by dt, and the V dot del V vector was actually the net outflow of momentum part of the equation. Just a small side note that V dot del is not equal to del dot V. You can recall that for constant rho, del dot V is the coordinate equation and this is equal to 0. V dot del is not equal to del dot V, and that is because V dot del is Vx del by del x plus Vy del by del y plus Vz del by del z, and del dot V is actually del Vx by del x plus del Vy by del y plus del Vz by del z. So here the velocity is within this operator in this side, and there is something missing here for this to be valid. That's why this is an operator. V dot del is an operator and it acts on this velocity vector in Navier-Stokes equation. So do not forget that V dot del is not equal to del dot V. Okay, so I hope that this sort of gave you some idea of how we derived this. We derived rho del V vector by del T plus V dot del V vector by doing rate of change of momentum plus net outflow of momentum per unit volume. If you cannot recall this, I highly recommend that please go through the lecture notes and derive this yourself. It will really help you in understanding Navier-Stokes equation once you derive this yourself. And you only have to derive it in one direction. The rest it can be generalized. Okay. So now let's go to the right hand side. So right hand side has three terms: minus del P plus mu del square V vector plus rho G vector. Okay. So the rho G vector is basically nothing but gravitational force per unit volume. Per unit volume, and you can basically just think of this as mg, which is generally the force of gravitation per unit volume, and that just becomes rho G. So this is pretty straightforward. So basically in this Newton's second law, the summation of forces, we are saying that there is one component of this is gravitational force, which is always act on a fluid element, and that is just rho G vector, and we can write it as, think of it as mg vector per unit volume. So it's pretty straightforward. But one of the terms we used was that this is a body force. Body force means it acts on the volume. It acts on the entire volume, so it's a body force. But the rest of these forces minus grad p plus mu del square v vector are actually surface forces. So they do not act on the entire volume, but they act on a surface. So that's the difference between these two. We generally use these two terms minus grad p plus mu del square v vector combined because they are combined surface forces. Okay, so the derivation of rho G vector is straightforward. We don't have to worry about it, but we need to understand how this part of minus grad p plus mu del square v came along. So for that, we go back to what we had introduced in class, which is the sigma tensor. This was sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma z. We said that we need a tensor to describe these surface forces is because for tensor we need two directions, and we need two directions because for any surface force, one direction is for direction of surface and the second direction is basically direction of force. So that's why we need a tensor, because we are dealing with two directions. First, we need to define a surface. For any surface force, you will naturally need to define a surface first, right? Before that, you cannot find any force. So you need a surface, and you need to define that surface by using a direction of the surface, or basically in this case, basically it will be the normal to the surface. Similarly, you also need to define the direction of the force because you're trying to calculate a force. So you need two directions, and that's why we need a tensor. So let us take any element. Let's take the sigma xy of this expression. So we said that the first subscript is actually the direction of normal to the surface, and this sigma xy is the direction of force. Okay. So whenever you will need to define any force from a surface, you need to have a tensor involved. So we basically introduced this tensor called the surface stress tensor, and we said that it has 9 components because we need 2 directions, one direction of normal to the surface and one direction of force. Okay, so now how did we get this minus grad p plus mu del square v from the sigma tensor? So let's first go back to our this element fluid element where we will write in the force balance. So as we have, just to recap, we had said that the left hand side came from writing the rate of change of momentum plus net rate flow of momentum per unit volume. The rho g vector came through the mg per unit volume, or mass times gravity force, or the gravitational force per unit volume. Now we are going to this minus grad p plus mu del square v part. So we said that this is the surface contribution of the force. So for the surface contribution of the force, we basically have this minus grad p plus mu del square v vector term. So to find this value, we will go back to our sigma tensor and start discussing the force in each direction. So we define this new vector called S vector, which has, this is S vector with the normal n vector is the force exerted by fluid on a surface with normal as n vector, and then we define this as n dot sigma, or nx nx ny nz, and we have a tensor here sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. Just to clarify, this is force per unit area, the Sn. So basically what we are saying here is that if we know the surface orientation, we know nx, ny, nz. So if let's say n vector is ex, then this surface has an outward normal in only x direction, or this is in the yz plane. So if this is y, this is z, then you will have a normal like this. Then if n is this, then the surface force per unit area can be calculated by nx, ny, nz times this multiplication with this stress tensor. In the lecture, we went through the entire each step and calculated this tensor. So this will now become a vector from a tensor. We calculated the entire vector, and we discussed how we can actually do it for a general surface. You can imagine for something like n equal to ex, this will become 1 0 0. So you will have force of we will have three directions of the force. So for n equal to only ex, the S vector for ex will become 1 0 0 times sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. And if you do this, you will actually find this will become sigma x x ex plus sigma xy ey plus sigma xz ez. And basically what I'm doing is I'm taking this vector and multiplying with by element on this and adding. So this is sigma xx plus 0 times sigma yx plus 0 times sigma zx. Add and have ex here. This is obviously just sigma xx. Then I take and multiply with this vector and add and do the same thing. And you can see that all this component have x here, x x here, because the normal is only in the x direction. The normal here is only in the x direction, right? So that's why you only have x here, and the direction of force can be anything. Direction of force can be x, y, z. The first subscript is only x because the surface normal is only in the x direction. So this is how we go from a stress tensor to a force per unit area. Given that we have defined the surface with normal nx and y and z, or for an example of n equal to ex, this is how your force will look like. So now what we did in the class was that we calculated the surface force for all the 6 surfaces in only in x direction. So you will have the force in different directions, but we only calculated in x direction. So for instance, in on this surface you will have force on this surface you will have force in x, y, and z. We only took the x component of it. On this force you will have x, y, and z. We only took the x component of it, and we did it for all the 6 surfaces. And what we said was that if you calculate that and if you generalize this, that contribution of Sn, which is already per unit area times area. Let me write this properly. So if you do Sn into area per unit volume, which is what we want because we want force per unit volume in the Navier-Stokes equation, that actually comes out like this. So we calculated it in the x direction and then we generalized it in all the 3 directions. And this is what it is in your Navier-Stokes equation. So if you have something like this, our Navier-Stokes equation actually then becomes rho into del v vector by del t plus v dot del into v vector equal to del dot sigma tensor plus rho g vector. So this is also Navier-Stokes equation. However, this is in terms of sigma stress, and we want it in terms of pressure and shear stress. So what we do is that we write this sigma tensor as minus p 001 plus tau So basically what we are saying is that from this sigma tensor you can go to pressure and shear stress, 2 different components. This is the pressure part and then the shear part by using this breakdown, or in short form you can write this as minus p Kronecker delta plus tau. This is the unity vector and tau is this stress. And we discussed in class that this is negative is because of compressive, and you only have diagonal elements here because this is all the pressure force is always normal. So in the pressure component of the force, the surface normal direction and the direction of force will always be same. So you cannot have something like sigma xy where you have direction of normal to the surface being different as direction to the force. You always have pressure acting normally, so you have only the diagonal part of this as being non-zero. And then you have all the 9 components in the shear stress part. So if we substitute this in the equation above, we will get something like minus grad p plus del dot tau plus rho g vector. Okay. Now this del dot tau vector can be further broken down, and to do that you can write that tau is actually 2 mu gamma, where mu is the viscosity and this gamma vector is the strain rate tensor. So as you can see, we are introducing a lot of new variables in this derivation itself, so that's why it's a very long derivation. Where gamma is actually this is the transpose, where gamma is made up of another tensor, which is the del and v. So this is an outer product. So during lecture it became clear that students feel that this is a dot product or some product, but this is an outer product, which means that if you multiply del with v vector, this is actually a tensor. So I refer you to review mathematics notes. They have been uploaded on the website, so you can just review notes on operators and you'll sort of get what I'm saying. But basically this is some outer product plus sometimes it's tensor by half. So the strain rate is a symmetric tensor. In other words, if I write strain rate in terms of exactly giving you what it is made up of, it is symmetric. So you have read in your maths courses about a symmetric matrix. Long tensor. We'll just quickly go through each term because this is something we did not discuss in detail in class. So I refer you to the book just in case this is becoming a little confusing. This has 9 elements, the strain rate tensor, but these two values are same, these two values are same, and these two values are same. So basically the ij component is equal to ji component in a strain rate tensor, and that happens because we have written it in terms of transpose being added, so it naturally becomes symmetric. So in other words, if this tensor is symmetric, the tau vector is also symmetric. So this is very important that you will be probably in any question or any problem that you have to solve, that you may know a velocity profile or you may have found a velocity profile. In that case, once you have the velocity profile, you can actually write the strain tensor. From that you can actually extract out the stress tensor. So please note that this is very important, that if you have the velocity profile or if you have calculated the velocity profile, you can write the strain rate tensor and then calculate the shear stress tensor. And because gamma is symmetric, tau is also symmetric, and that is sort of because of the definition of gamma, that tau is also symmetric. So once we have this definition, the tau is definition, and if we assume mu is constant, when we take the derivative we can take the mu out, uh, and that is something again uh, which you can see that if you have gamma here, there's two factor here and half in gamma, so this gets cancelled. You can take the mu out, and because there is one del here, another del here, once you put it in the Navier-Stokes equation, or sorry, the balance equation, it becomes the Navier-Stokes equation. Okay. This comes because when you put tau as 2 mu gamma, where gamma is this half del V plus del V transpose, and you simplify, this actually becomes del square V vector. So there are a lot of things that have been discussed in this video. I'll again recap one by one on each term. So first we said this is the entire equation. The left hand side is made up of the rate of change of momentum plus net outflow of momentum per unit volume. The net outflow of momentum per unit volume is the new term that comes out because of the balance on 6 surfaces. This happens in fluids because we have an open system. So again, go back and derive each term and derive it in one direction, which is x direction, and then you can generalize this. Uh, we also made a side note that v dot del is not equal to del dot v. Okay, this was the left hand side of the Navier-Stokes equation. In the right hand side, we had rho g vector as the mass times gravity per unit volume. So that's just a body force. Then we go into surface forces, which are more complicated. In surface forces, we introduce sigma tensor, which is 9 components because we need two directions: one the direction of normal to the surface, and one direction of force. If we have the sigma tensor, and if we have been given a surface. If we have been given a surface, we will know the n vector. From there, we can calculate force per unit area, or known as small s vector, at a given surface, which is n vector. So we take a dot product of n vector and sigma tensor. The dot product of a vector and a tensor will give us another vector. So this is the entire. If you have been given nx, ny, nz, and if you have the entire stress tensor, you can multiply piecewise each element and then add them to get the x component. You have done these multiplications in your mathematics course, so please go ahead and try this yourself. For a simplified case where n is only ex, we showed that this Sn(s) of ex becomes sigma xx ex plus sigma xy ey plus sigma xz ez, where the first subscript is always x because the direction of the normal is only ex. If you had direction which was tilted, you will get components obviously which also have a y and z in them, but it is only x right now because the normal is just ex. Okay, so now that we have s, or we have force per unit area given a normal, we said that in class what we did was we went and derived the x direction of force on all the 6 surfaces, and when we did per unit volume basis, we got the simplified expression of del dot sigma double bar, or sigma tensor. Now if we put it back in our equation, this will become del dot sigma, the surface component part, but we can break down the further sigma stress into two parts. One is the pressure force, which is compressive and only acts normally, and then second is the viscous stress part. For the viscous stress part, we said we can write, and we can put this back, and this will become del dot tau here. For the viscous stress part, we can write tau as 2 mu gamma, or this is the strain rate tensor. Strain rate tensor is outer product of velocity and gradient and the addition with transpose, so that's why it becomes symmetric. If you expand the strain rate tensor in Cartesian coordinates, you can see that these two components, this component and this component is same, or sigma ij is equal to sigma ji. Let me clarify this here. Sigma ij is equal to sigma ji, and since sigma is symmetric, tau is also the symmetric. Okay, so once if you have been given a velocity profile, you can calculate strain tensor and you can get back the tau tensor. And then just in case if there is any confusion, the strain has units of second inverse. That's why you have velocity over length here. So this strain is equal to, when we used to write when we say stress scales as mu u by h, where u is the velocity and h is the height. This u by h is basically the strain rate, or the second inverse unit. So that is what this whole expression is, but this is in 3 dimensions and in terms of partial derivatives, and it is symmetric, which makes tau symmetric. So if we put that back here, we get back rho del v by del t plus v dot del v vector and minus del p plus del square v vector plus rho g vector, which is our Navier-Stokes equation. Remind yourself again that this is for constant rho and mu. This is the body force component, this is the shear or the surface force component. This is the pressure part, this is the shear part, and this is the rate of change of momentum plus and outflow. So we basically, the idea of this video was for you to go back and revisit Navier-Stokes equation step by step. Please take out time and derive everything once yourself, and once you will do that, you will see that uh, you will be able to really understand problems much better just because you have a better grasp of the whole equation. So I hope this video was useful. We'll also upload another video on deriving why tau is symmetric, and hopefully you'll find that useful also. So please feel free to give us any feedback, and see you in the next video.